Hello everyone, welcome to the first lecture of week 3 on power network analysis, in which we will continue our discussion on synchronous generators. In the previous lecture, we had discussed about the basic phenomena of how voltage is induced in the stator windings of a three-phase synchronous generator due to the rotor windings carry DC current and the rotor rotating at synchronous speed, which is driven by the turbine or the prime mover, as a result of which the stator windings experience sinusoidal time varying flux linkage, and by Faraday's law and Lenz's law, a voltage is induced in these three-phase stator windings. Coincidentally, these induced voltages are inherently positive sequence voltages, and as long as the synchronous generator is not feeding in any electrical load, there is no notion of the stator winding reacting to this rotor flux which is present through the air gap. So when the rotor windings carry any current, that is, they are feeding in some electrical load, the stator windings also carry three-phase balanced currents, which leads to creation of stator MMF, which opposes the rotor MMF, and as a result the air gap net MMF, magnetomotive force, is combination of rotor flux MMF and the stator flux or MMF. So in today's discussion, we will build up on these discussions which we had in the previous lecture and try to understand how would the electrical equivalent circuit of a typical cylindrical pole synchronous generator look like. What are the governing equations in phasor domain that help in understanding the steady state behavior of a synchronous generator. So just to recapitulate, the rotor current, which is DC current, IF, it induces a rotor flux phi f in the air gap, and this rotor flux is rotating at the same speed as the synchronous speed of the rotor, which in a way induces EF. In phasor domain, the corresponding RMS value is ERMS in the stator windings. And when the generator is loaded, the armature currents also exist. That means IA is not zero. I'm choosing IA not to be the current for phase A, but in fact IA represents the armature current or stator current, and it is the per phase equivalent representation. It is not the phase A current. So as a result, when the generator is loaded, there exists non-zero armature current, which also creates its own flux in the air gap, and which we call that flux to be the armature flux phi A, which is nothing but the effect of armature reaction. And it has two components. One is the minor component, which is known as the leakage flux. This leakage flux is linked only to the stator in form of core loss components, magnetization component. And the other major component, which is the reaction flux, it links the stator winding, the air gap, as well as the rotor windings. So the armature reaction effect, which we had discussed in the previous lecture, was essentially the effect of this reaction flux. We had not considered the effect of the minor component of this armature flux, which was the leakage flux. And as a result, since the air gap consists of the rotor flux as well as the reaction flux from the stator, so the net air gap flux is vector combination of the rotor flux phi f as well as the reaction flux from the stator winding. So if we have to plot these fluxes, which we had also seen preliminarily in the previous lecture, if we have to plot these fluxes on a phasor diagram, then assuming the flux, rotor flux to be my reference by Faraday's law, the induced EMF is time derivative of the corresponding rotor flux. So basically the induced EMF leads the corresponding rotor flux phi f by 90 degrees. And consequently, because of the armature current, which happens to be non-zero when the generator is loaded, there also exists this major reaction flux from the armature or stator, which is known as phi AR. And in the previous lecture, we had seen phi gap to be the vectorial combination of phi AR and phi F, which for timing I have not shown in this phasor diagram for the sake of simplicity. The important part to understand here is the induced EMF and the armature reaction voltage, they don't go one by one. They are not aligned to each other. It is thanks to the nature inherent behavior or law given by Lenz, which is called as the Lenz law. Every action has opposite reaction. So since the rotor flux is inducing voltage in the stator is trying to oppose this induction through this reaction voltage, and hence the effective stator voltage which might appear on the stator voltage windings is vector sum of induced EMF EF and the opposing action of armature reaction flux because of the negative opposing effect by Lenz law. So if we have to plot the reaction voltage EAR on the same phasor diagram, since armature current is non-zero and the reaction flux is the major component of armature current, so phi EAR is in collinear direction with IA, and as a result, like induced EMF leads the corresponding flux by 90 degrees, the armature reaction voltage would also lead the reaction flux by 90 degrees, and induced or the armature voltage or stator voltage ER is vector sum of EF and this negative minus ER. So this is the dotted line which is indicating minus ER. So when we superimpose this on tip of ERMS, we get ER as EF minus EAR. Please remember, these are all vectors or phasors. They are not simple scalar quantities. As I have already mentioned, phi AR will be in collinear or in phase with stator current being the majority component. So essentially, the induced reaction voltage, it leads the corresponding armature reaction voltage by 90 degrees. So this lead effect of voltage with respect to current, it can be represented through a analogous inductive circuit where if suppose XAR is the armature reaction reactance or magnetizing reactance, then induced the armature reaction voltage, which is EAR, can be mathematically represented in terms of IA through the help of the inductive reactance, which is the armature reactance or armature reaction reactance. So JXAR IAR is nothing but EAR. And now if we put in the value of armature reaction voltage into the effective stator voltage, we get the equation which is underlined over here, and when we reorient it, so induced EMF EF, these remember these are all phasor quantities being measured with respect to a particular reference. So induced EMF is nothing but the effective stator voltage plus the voltage drop across the armature reaction reactance or magnetizing reactance. The stator windings, they will definitely have some resistance. We have also not considered the effect of leakage flux, which is linking only to the stator and not forgoing beyond the air gap. So we also have to consider those voltage drops, and effectively we will also have to have an evaluation of what is the net terminal voltage per phase terminal voltage across the synchronous generator winding. So if the stator winding has a non-zero resistance, which is usually the case, the leakage reactance XAL is accounting for the leakage flux, and there is also a terminal voltage per phase VT across the synchronous generator. So in addition to the induced EMF and the armature reaction reactance, which in a way leads to the stator effective voltage, this ER induced voltage is responsible for voltage drop across the leakage reactance. It's also responsible for voltage drop across the winding resistance, and then effectively we would have VT as our per phase terminal voltage. So in a way, this represents a equivalent circuit, which is the one shown over here, the equivalent per phase circuit of a typical cylindrical pole synchronous generator. Now, the reason why I am emphasizing about cylindrical pole generator, it would become obvious in the next few slides to come in. So effectively, if we have this as our equivalent circuit representation for a cylindrical pole synchronous generator, we can also have typical expressions, mathematical expressions, which can explain how this equation or circuit looks like in terms of a equation. So if we put all on that, then remember we had defined EF to be sum of ER and this voltage drop, where if we reorient, ER is nothing but Vt plus Ia, the voltage drop across winding resistance and leakage reactance as per the circuit which is shown over here. So if we put in all those variables numbers there, effectively we have induced EMF is nothing but the terminal voltage across the per phase terminal voltage across the synchronous generator plus the voltage drop across the winding resistance and the leakage reactance and magnetizing reactance, they together can be combined as the reactance XS, which we call as per phase synchronous reactance, which is basically combination of magnetizing reactance, which is the major component, and the minor component, which is the leakage reactance XAL. So if we put in, so effectively this is our governing equation for a typical cylindrical pole synchronous generator. All the above equations, the one which are shown here, the currents and voltages, they are all phasor domain quantities with some reference quantity as their corresponding phasor reference. So if we put in or choose the terminal voltage, per phase terminal voltage as the reference for measurement of all other phasors, then the induced EMF will have an angle delta with respect to terminal voltage, which on this phasor diagram is the angle which is being marked like this, delta. And depending on the load which is connected to the synchronous generator, assuming that load to be an inductive load for the phasor diagram which is shown over here, which means the current is lagging the terminal voltage. So the angle between terminal voltage and current is theta, which is what is shown over here, Ia at an angle minus theta. We can represent or draw the phasor diagram which in a way correlates this entire equation, and induced EMF is nothing but the terminal voltage plus the voltage drop across the winding resistance plus the voltage drop across the corresponding synchronous reactance, where ERMS is typically 4.44, N being the number of turns on stator, phi f is the maximum flux linkage from the rotor to the stator, and F is the corresponding source frequency, which depends on the synchronous speed. Delta is the torque or power angle as I have marked here. Theta is the phase angle or the impedance angle between the terminal voltage and the current. So this is just a slide which recapitulates what we had discussed in the previous few slides. Remember, we are choosing the per phase terminal voltage as the reference for all other phasor quantities. One thing to note here is that the phasor diagram which we have seen here, it is specifically for a cylindrical rotor synchronous generator. Things will become little different when this synchronous machine behaves as a synchronous motor. The difference is the induced EMF is always leading the terminal voltage in a synchronous generator. That means the torque angle or the power angle is always a positive quantity for generators, whereas in a motor, the expression which is shown over here, it transforms into the expression as Vt, which is the terminal voltage, should be equal to induced EMF plus the voltage drop across the corresponding winding resistance and the corresponding synchronous reactance in case of a synchronous motor. In a motor, the objective is to convert electrical input power to mechanical power. So the current direction is reversed, as a result of which induced voltage is output or resulting of the terminal voltage which is applied as input to the synchronous motor. So with that equation, what happens is the induced EMF EF, it tends to lag the corresponding terminal voltage, which means power or torque angle becomes negative in case of a synchronous motor. The same aspect is essentially shown over here, written over here, and the other quantities, they remain the same as we have discussed in the previous few slides. So the phasor diagram which I have discussed here or shown over here, in this inherently we have chosen the rotor flux to be our reference. Rotor flux being a DC flux or coming from the DC current. So essentially we can have a phasor diagram where we have only AC quantities And with Vt as our reference, terminal voltage as a reference for phasor, we can again redraw the phasor diagram, which would look like this for a cylindrical pole machine, with this KVL equation being the governing equation for a synchronous generator in cylindrical pole rotors. For salient pole rotors, where things become little different and interesting, is that in a cylindrical pole rotor, we have well understood that the air gap length or the path between the direct axis and quadrature axis, they remain the same. So as a result, one would think that, oh, if I have to measure the reactance along any length of the air gap in a cylindrical pole rotor, where the synchronous reactance is inversely proportional to the air gap length, lesser is the air gap length, more would be the value of reactance, indicating more linkage happens in terms of flux between stator and rotor. One would imagine that the synchronous reactance would remain constant along the direct axis and quadrature axis for cylindrical pole machine. That's theoretically possible. In practice, synchronous reactance never remains as a constant quantity, thanks to the nonlinear open circuit characteristic. One of the reasons being the nonlinear open circuit characteristics of the synchronous generator, and also the nonlinearity involved in stator cores and rotor cores of the synchronous generator. So as a result, the synchronous reactance is not a constant quantity. It has variation. It has nonlinear variation with respect to machine's magnetization behavior. We had briefly discussed about the open circuit characteristic in the previous few slides, on the previous few lectures of synchronous generator, where we saw that the OCC is not a linear curve, and that nonlinearity is responsible for the synchronous reactance not being constant, one of the reasons. The other reason is the rotor slots, they are distributed. Same is true for the stator slots where windings are placed. So effectively, the distribution of these stator and rotor slots for windings, it creates variations in the air gaps along the D and direct and quadrature axis, even in a cylindrical pole machine. And furthermore, in salient pole machine, the direct axis reactance Xg is much more than the quadrature axis reactance, because along the direct axis the air gap length is small, and on the quadrature axis the air gap length is higher. So it is furthermore relevant that the synchronous reactance will not at all be uniform in a salient pole machine because of the non-uniform air gaps. So as a result, we have different values of synchronous reactance in a salient pole machine. So the question then comes is, what should be the governing equation in a salient pole synchronous generator? Because as per this discussion, where the different values of synchronous reactance exist along direct and quadrature axis in salient pole machine, this beautiful equation will no more be applicable for a salient pole machine, because the reactance value itself is going to be different. So what is the discussion? What should be done? So one thing, so let's go step by step. How do we consider the effect of rotor saliency in understanding the steady state behavior of the salient pole synchronous generators? So one thing is pretty sure, that the direct axis quadrature, the direct axis reactance Xd is much more than the quadrature axis reactance, because the air gap length here is much smaller compared to the air gap length along the quadrature axis. In order to consider this rotor saliency, we have to have a consideration of these two different reactances, that is for sure. So let us see how do we do that. So what we do is, we resolve the stator MMF, specifically the armature reaction MMF, not the leakage component, along two axes. One is the direct axis, the other is the quadrature axis. The corresponding stator MMF resulting from direct axis current is not aligned with the corresponding stator MMF coming from the quadrature axis reactance. So basically what we do is, we indirectly decompose the armature current or stator current IA along direct axis, which we call as ID, the direct axis current, and IQ, which is the quadrature axis current. And these currents, they look something like this. The quadrature axis current IQ is parallel to the induced EMF phasor EF, whereas the direct axis component is perpendicular to the quadrature axis component. Now let's spend some time here why this phasor diagram is applicable for salient pole machine. In order to understand this, we'll probably have to go a few slides back. So let's do that. What we saw here in this particular phasor diagram, if we see, in a cylindrical pole machine, where the air gap is more or less uniform, and assuming the synchronous reactance is not drastically different compared to a salient pole machine, we have one single armature current which is leading to the major armature reaction flux, and as a result of which the corresponding armature reaction voltage is perpendicular, which is this orange line, perpendicular to the corresponding armature reaction voltage. Now in case of salient pole machine, where the IA current, armature current, is being decomposed into direct axis current ID and the quadrature axis current, which in a way would also have their corresponding armature reaction voltage. So let's say if we mark the EAD as the armature reaction voltage because of the direct axis current, and EAQ as the quadrature axis reaction voltage because of quadrature axis current, how would these reaction voltages look like for a given salient pole machine? Now it is for sure that the induced EMF and the corresponding reaction voltage, they don't align with each other. They are phase apart from each other. And if we remember, in a salient pole machine where the rotor is tapered with salient pole, with north pole let's say being marked here and south pole being marked here, the magnetic axis along which the air gap is minimum in a given salient pole rotor, we call it to be the direct axis component, whereas the quadrature axis component is perpendicular to the corresponding direct axis component. So now if we look at the salient pole rotor, one can easily understand that the induced EMF, which is result of the rotor current, it is aligned along this direct axis. So let's say if we mark EF, which is also ERMS at an angle delta, then the corresponding direct axis component reaction voltage would typically be in the opposite direction to the direct axis current. So let's say if ID is the corresponding armature component of the direct axis, then minus EAD should be opposite to the induced EMF, and consequently the quadrature axis reaction voltage, which is perpendicular to the direct axis component, would more or less like be along this particular axis. Let's say if this is minus EAQ. Then if we correlate these induced EMFs, reaction voltages because of ID and IQ components of IA, the corresponding direct axis current, it should lead the corresponding minus EAD. So essentially ID current should be aligned along this particular axis, whereas IQ current should be aligned along this particular axis in correlation to the corresponding currents which have been shown here for the corresponding cylindrical pole machine. So if we correlate or superimpose this, what we see here is that induced EMF and quadrature axis current, they are parallel, whereas the direct axis component is perpendicular to the induced EMF direction. So that is what is the reason behind having this as our phasor diagram for salient pole machine. And mathematically we can define ID to be the sine component of armature current, which is dependent on the impedance angle and torque angle, and the corresponding quadrature axis current is cosine component of armature current, which again depends on phase angle between voltage and current, terminal voltage, and the power angle. So if we have to write an equation which mathematically represents this phasor diagram, then this is what the corresponding equation looks like. The first two terms, they remain similar to the terms in cylindrical pole machine. The last two terms, they are replacement of JXS IA in cylindrical pole machine, and the induced EMF is leading the terminal voltage for generator. So if we break this equation along two components, along two axes, one along the Q axis current IQ and the other along the D axis current, we can get two analogous equations. The first equation is along the Q axis. How do we get it? It's very clear that if we look at the vectors which are aligned along IQ, then we have EF, and then we'll also have Vt cos of delta, the component of Vt along the Q axis, which is Vt cos delta. And then we have JDXD, which is a term sitting over here. And then IARA will also have a component along this IQ axis, which would depend on the cosine of theta and delta. And along the direct axis, if we see, which is along this component, we have IQ XQ as one component, and the other component would be the component of VT along IQ, which is VT sine delta, and the component of IARA, which is this component. So that's how we get two analogous equations. Unfortunately, we cannot have a single equivalent circuit where we can have two different reactances in series with two different currents in series, and that's the reason why you would not see exact equivalent circuit for salient pole machines and typical references or textbooks. That's all for today. In the next lecture, we will take up the discussion on evaluating power expressions and capability curves for synchronous generators based on the equations which we have seen over here. Thank you.